thanks for the introduction. Thanks for having me in Vienna. The goal today is to give you a little bit of a mixture of theory and practice. Right? Now, I'm going to argue very strongly for that. I spent most of my life in the role of developing methods and tools for about 30 years now. And it normally takes about 4 or 5 years of working with the theory, thinking about it, making notes, talking with people, before you're ready to launch a method or tool. Then it takes about 3 or 4 years of practice to get it right. Right? Part of the major problem we got with the Agile movement at the moment is they think the last 3 projects that they did and which they half remember can constitute a universal method which can be codified and from which they can sell certification. So part of what I'm going to argue now, and the craft element here, is we need to be far more disciplined in what we're doing. If you don't have sound theory, you can't scale practice. If you don't have practice, theory means nothing. You need a combination of the two. If you want me to put it in simpler terms, if you don't understand the why of what happened, you can't scale the how. You have to understand why something worked, otherwise you get into major mistakes. So what I want to do is to give you some of the background theory on this and talk about some of the methods and tools. And really the context is this slide here. And I'm not arguing against flow per se. What I'm arguing against is a linear flow in one direction. So we've trended sheet software development as these guys know what they want, they tell us what they need, we then tell them to ignore us for a bit because we're the clever IT people and we really don't like users anyway, if we're honest about it. And then we'll produce something and they'll be deliriously happy as a result. Everybody familiar with that? I've been in IT all my life, and I think we developed user requirement documentations and entity flow diagrams so we could hold users accountable for something we could prove they wanted. But the minute you deliver it, they discover they wanted something else instead. Now, in my context, the users are actually right there because the potential of technology is far higher than any user knows what to ask for. Yeah, so users tend to make requests within the context of what they currently understand, or in terms of what we call false utopias. That's the big problem with machine learning at the moment. I don't call it artificial intelligence, it isn't, it's machine learning. Yeah, is that it's actually getting us to buy into a utopia which isn't even defined. We just say, join on this journey and life will be wonderful regardless of the implications. Yeah? So what I want to talk about is making things a lot more messy. Is how do we co-evolve the capability of technology with unarticulated user needs? Things that users didn't know technology can do. How do we create software ecosystems in which users will discover capability which they weren't previously aware of and which we ourselves didn't design? And that's a very different way of framing the problem from the traditional manufacturing model and the manufacturing metaphors that you see all the way through software development. Yeah? Now, as I say, I want to make this practical with some tools and also with some frameworks and theories. The general approach for what we work on is called naturalizing sense-making. That's the sort of generic term. So I define sense-making, and I spell it with a hyphen. Sorry, I'm also an academic, and hyphens matter for academics. If you see it without a hyphen, don't panic, but it does matter, right? I define sense-making as how do we make sense of the world so that we can act in it. And with that comes a concept of sufficiency. We will never know everything we would like to know in order to make a decision, but we need to understand what type of decisions can we make based on what we currently know, or if we're in conditions of extreme uncertainty, and I'm going to go through a statistical model on this later, we need to have a process which can handle the uncertainty rather than trying to plan for it in advance. This actually comes from a lot of military work. You need to have mechanisms which are resilient. They're designed because they have utility and they can respond in ways that you can't anticipate. And I'll build on that as I go through. The naturalizing means to root what you do in the natural sciences. Yeah? My background is physics and philosophy as a joint major. That gives me a physicist's contempt for social scientists. They never have enough data to form any valid conclusion anyway. And management scientists are a more extreme subset of that. And you don't want to know what philosophers think about social scientists. We tend to get drunk before we confess to that one. Right? But basically, what we want to do is say, in natural science, there are things that we know which have been subject to repeated experiments and third-party review. Now, the huge complexity of a human system can't be subject to 19th century concepts of empirical research. It doesn't work. There are just too many variables. Yeah, and that's actually one of the problems with empiricism in the software movement, is they become over-dependent on their personal experience and their personal perception of what happened, and that is really dangerous when they try and scale it. Yeah? But there are things that we know about how human beings make decisions and about how systems work, which in effect act as constraints. And I'll give my favorite illustration of that now, which is kind of like this one. It's a famous one, I use it a lot. If you take radiologists, and for reasons we don't fully understand, radiologists are subject to these experiments. I think at some stage in their past they did something terrible and the cognitive neuroscience community has never forgiven them, so this is revenge. So you take radiologists, you give them a batch of x-rays. On the final x-ray you put a picture of a gorilla, which is 48 times the size of a cancer nodule. 83% of radiologists will not see it, even though their eyes physically scan it. And the scary thing is the 17% who do see it come to believe they were wrong when they talk with the 83% who didn't. No? Scientific fact. That just invalidated any systems analysis anybody does. You will not see what you do not expect to see. And the reason for that is very simple. The most that anybody in this room scans of available data is about 3 to 5%. That's the most. Yeah? That then triggers a series of memories, which are cognitive, physical, and social, through the stories we hear in our communities and societies. All those memories in a sort of complex melange. It's called conceptual blending. They get blended together in nanoseconds, and the first blended pattern, which appears to fit, we apply. So we do a first fit pattern match. We don't do a best fit pattern match. We satisfy, we don't optimize. Now you can see why this evolved in humans. If you think about the early hominoids on the savannas of Africa, something large and yellow with very sharp teeth runs towards you at high speed. Do you want to artistically scan all available data, look up a catalogue of the flora and fauna of the African veldt, and then identify best practice case studies on how to avoid lions? By that time, the only document of any use to you will be the Book of Jonah from the Old Testament, which is the only example I've found of an escape manual from the digestive tract of a large carnivore written by a survivor. So we evolved to make decisions very, very quickly based on a partial data scan, privileged in our most recent individual and collective experiences. That is a straight fact. You cannot train people not to do that. So that means we need to develop methods and tools which work with that rather than work against it. Yeah? And I'm going to go through some of those in a minute. And this is kind of like illustrates the point, yeah, in terms of the way it works. So that's kind of like one thing we know. We also know that individuals, and I'm going to build on this later, we evolved to make decisions. We're actually really bad as individual decision makers. If you really want to upset anybody who's got a cognitive science background, say that you're taking Malcolm Gladwell's book Blink seriously and you will never be invited to dinner again. Gladwell is a classic example of a journalist who picks examples to support a compelling hypothesis. Now, there's quite a few books around that, so I might as well go for it. Reinventing the Organization is another example, where he takes examples of cases which support his proposition. He doesn't take the aspects of those cases which basically say it doesn't work in practice. Okay? So this desire to basically say, oh, I love this, it's wonderful, but it's a really dangerous tendency. We need a much higher level of realism, yeah, in terms of what we're doing. So if we're going to sort of build on that and actually make something work with it, as I say, we can't afford to have this very idealistic, this is how I would like people to be, and therefore the world will work. Klein, myself, and others now say there's no such thing as a cognitive bias. They're only heuristics. All of our so-called biases have evolved because they reduce the energy cost of making decisions. Most of the time, there will not be a picture of a gorilla in an X-ray. So why would you think there would be? Yeah? Most of the time, going with the flow, responding to the biases of the community you're in, sort of works. Yeah? So all of human evolution, in fact, evolution in general, tends to reducing the cost of energy consumption. If I want to put it really simply, and again, I'm going to build on this, if the energy cost of virtue is lower than the energy cost of sin, you will get sin. So changing the energy gradients of a system so the things you want to happen are easier is a key part now of understanding how we architect for future software developments. Anybody in UX knows this already. You need to make it easy for people to do things rather than having to reinvent or recreate themselves from scratch. So that's going to be a key principle of this talk. And what that means, and one of the consequences of that, is that fundamentally, you can't have recipes. Well, I can give you a recipe for failure, but all success is different. Yeah? And that's the problem. We've got an industry which loves recipes and has very few chefs. And that's a really important difference. A recipe book user is fine as long as you've got all the right ingredients and all the right equipment and lots of time. But if you haven't got the right ingredients and you haven't got the right equipment and you haven't got much time, a chef will always produce a good meal, whereas a recipe book user will fail. And the reason is a chef understands the theory of taste and has done years of practice. They have theory and practice, what Aristotle calls Sophia and Pronesis. They have both combined. Yeah? So again, this is this argument to shift away from following a recipe into understanding the principles and developing them in practice. So that leads me on to complexity and Cynefin, and I'm going to do 2 frameworks in this session, or possibly 3. I'm not going to do the full-blown Cynefin. There are 3 levels to Cynefin. I'm going to do the sort of level 1, basic one, and then indicate where you can go below, right, and follow through on that. Now, this works off the very simple principle that we can identify 3 states in nature. And by the way, that's the picture of the European Union Field Guide, which was actually to complexity management, which I was the principal author on. Rather ironic given what the English did to us. We blame the English for everything in Wales, all right, and generally we're right. You can get that for free from the website. You can download, you can have a copy, all right? So that's based on Cynefin, and a lot of the ideas are in that. So basically, the base form of Cynefin is quite simple. It says there are 3 types of system that we can find. And one is ordered, the other is complex, and the other is chaotic. Now, the easiest way I've found to explain that is to think of it in terms of solid, liquid, and gas. So at this point, I'm going to remind you all about latent heat, which, of course, you all remember from school, and nobody's forgotten the basic principles, all right? But basically, if I heat water up to 100 degrees, it doesn't immediately become steam. I have to put more energy in before it changes. That's called a phase transition. Equally, my kids always laugh at me because I can smell snow coming. I grew up in the country, I can smell snow. They can't. The physical reason for that is that actually heat is thrown out as liquid becomes solid, and you can pick that up at a slight olfactory level. Right? So that's called latent heat. It's a phase shift. Yeah, heat is thrown out, or energy is thrown out, or energy is needed to achieve the change transition. So an ordered system is highly constrained, everything is predictable, you know exactly what will happen. The same thing happens again the same way twice. There's no problem with recipes, they always work. Yeah? So that's solid in my metaphor. It's structured, it's rigid, you know what it is. Chaotic, and there are various definitions of chaos. It's one of those difficult words. It's used in physics in one way, it's used in complexity in a slightly different way, it's used in sociology in a different way, so you have to be clear. I'm using it in the more ordinary common language sense of the word. It's a system without effective constraint. So everything is up in the air. It's kind of like quasi-random. Yeah, so that's the way I'm using it. So there are no effective constraints. Well, that's kind of like a gas. And between those 2 states, you've got liquid, which is difficult to contain, but everything is connected. Yeah, the molecules aren't dissipative. They're all sort of connected, and they flow. So that's a nice, simple metaphor to understand it. So in an ordered system, I've got structure, I've got recipes. In a complex system, everything is connected with everything else, and I'm going to talk about how we manage those later. Yeah? In a chaotic system, which is only ever temporary in a human system, human beings do not like chaos. Chaos is a natural state, that's no problem. Human beings will impose order pretty damn fast if something becomes random. In fact, one of the key things is to recognize it earlier, because then you impose the order on the system. So those are the three types of system. Yeah? And then we got this interesting thing in the middle. You may remember that from your high school science, that there is a point of equal balance of pressure or temperature. It's called a triple point, where it's equiprobable whether something will become solid, liquid, or gas. Yeah? So you don't know which way it will go. And that in Cynefin is a central domain, which is called the aporatic domain. That may be an unfamiliar word to you. I gather every Greek school child knows it. It's the name for Derrida's definition is the one I like. He says, if you know the answer to a question, it isn't a question, it's a process. The only valuable questions are where you don't know the answer until you think or act differently. And that's called aporia, or an aporatic domain. And that's a really important domain in Cynefin, because it says that's where you should start. You should start by putting people into physical places, introducing art, introducing difficult questions, which force them to break the patterns of the way they're currently thinking and think differently about the problem. Remember the gorilla? You want to find the gorillas. Or you want to find the people who've seen the gorilla before they talk with the other people. Yeah? So in Cynefin, you start in that domain. You ask really difficult questions, and then things move into the other domains from there. Right? That's kind of like a base principle. And I'm not going to go to this in huge detail, but we divide order into two. And that's a separate one where it's clear and where it's complicated. And that's probably the version you most often see, yeah, which is the 5-domain version of Cynefin. I do find it amusing when people talk about the 5 quadrants in Cynefin. If you think there are 5 quadrants, somebody needs to go and address your education, but it's amazingly common. Yeah, fundamentally, Cynefin in that form has 5 domains. Yeah? In clear, you can apply best practice. In complicated, you apply good practice. In complicated, you can trust expert judgment. In clear, it doesn't matter. Yeah, because everybody agrees. In Austria, you drive on the right-hand side of the road. In England, we drive on the left-hand side of the road. Everybody agrees, everybody follows it, there's no dispute. And that's actually a nice place to be if you can get there. Yeah? Complicated is more different. Now, the danger on this is if you over-constrain a system which isn't naturally constrained, and that's why this boundary is shown as a cliff on Cynefin, i.e. you fall off it, is that basically you make things so rigid and so controlled that people don't follow the rules anymore, they work around it. And my favorite example of that is I survived 7 years in IBM. To be clear, I didn't volunteer, I was conscripted. They bought the company I was responsible for. And the first thing they did when they took us over is to ban alcohol and charge us for coffee. Now, we're a software development house. The coffee-alcohol cycle is critical to quality software development. Yeah? Nobody should be expected to talk with users without alcohol first. You then need coffee to sober up to write the code. Then you need even more alcohol when the users don't want you developed, going back to that point. Either way, we found ways around that. And then it got worse. They banned us for buying food for staff. Classic big company move, all right? We shouldn't be doing this. So, but now I'm C-level executive, all right? I've stopped coding years before. And I went into HR in IBM and said, look, last night, 2 o'clock in the morning, I got a phone call. I'm the duty exec. We've got an emergency service which has gone down, on VAX clusters, all right? And by the way, the reason I didn't tell them this is that you banned us from sending people on training because you said people could learn about operating systems from manuals, and that's actually why it's gone down an upgrade. But never mind that, don't fight that one, yeah? So I get called out 2 o'clock in the morning, and my job is very simple. I've got to keep people away from the systems programmers. The last thing they want is people saying, what are you doing? When are we going to get a result? Can I help you? Yeah? The whole role of executive management in a software crisis is to form an absolute barrier and lock away the programmers and let them get on with it and give them time. And there are all sorts of tricks around that, by the way. If you haven't learned the one about always ask users to go and do something, even if it's meaningless, because it will keep them occupied and they won't bother you, then you haven't really been around in software for long enough. You know? So either way, so I sat there and I said, well, so what can I do? So that's one of my jobs, and that's no problem. The only other thing I can do is keep them awake. So I've got to buy them pizza and Coke. And they looked really worrying at that point, and I said, hang on, that could have been misinterpreted. I said, I did mean Coca-Cola. And they sort of breathed a sigh of relief because they were getting worried about us by this point. And they said, okay, we understand that. So, and eventually, after some discussion, they finally agreed, yeah? And by the way, I'm using a Socratic technique here. If you're dealing with bureaucrats, never argue logically and reasonably. It won't work. You have to ask them questions until they contradict themselves. But remember what happened to Socrates. The people of Athens got so fed up of it, they voted for him to commit suicide, all right? So there are limits to this process. So they said, okay, we accept that may be necessary. Vice presidential approval 48 hours in advance. Now, at this point, you just stay calm. And you say, God, that's brilliant. We would never have thought of that. This is one of the major benefits of joining IBM. And then you realize that irony and sarcasm are deadly weapons because they don't take them seriously. I said, what happens on the very, very rare occasion where we don't get 48 hours notice of a major crisis? And they looked at me in this disturbed way, like it was my fault if we didn't get notice of a major crisis, all right? There was something disturbed in the process. And after a lot of discussion, they finally agreed, yeah? And they said yes in a way which meant no. Bureaucrats are really good at this. They said country general manager approval after the event. Now, if you work for IBM, you know that what this means is your expenses will disappear into the South Bank office, they'll never be signed, and if you complain about it, your name will start to appear on the wrong sorts of lists. Those lists which come out every quarter during a recession, right? So I gather, and I hasten to add that I didn't do this and nobody I knew would do this. Absolutely, we just heard about this on the rumour mill. The practice emerged of over-tipping London taxi drivers. Because if you over-tip a London taxi driver, so I'm told, they give you a blank receipt. The blank receipt was then filled in, I'm told, for the amount spent on pizza and Coke by the responsible executive and claimed as a taxi fare, which was legitimate, and a parallel set of books were kept so that other people could prove what they did when it happened. Either way, that sort of calmed things down. And I gave this example at a Scrum Alliance conference in Berlin some years ago. 3 people from IBM ran up to me with a wallet stuffed full of blank receipts and said, we're still doing that, did you invent it? Now, that's an example, and the danger of that is people have learned how to defraud the system. They've defrauded it because they just need to get the job done. And that's the massive problem in companies which are over-bureaucratic and over-structured. You know, the people who took Six Sigma too far, or as Gary Klein calls it, Six Stigma. Yeah, people who've taken the safe pill, which I won't go into the color of the safe pill. Yeah, they've got so much structure that actually people have to work around the system or be selective to get it to work. That consumes a huge amount of energy, and ultimately the system will collapse. It will descend into chaos. Yeah? So that's a key principle on Cynefin. Now I'm going to go more into complexity now. There's the third level of Cynefin adds liminality. And Cynefin, like any good framework, you should be able to understand it quite quickly. And as you understand it, you should be able to dive deeper and deeper and get more meaning. Yeah? So I'm not going to go into that at this stage. So that's kind of like the basic Cynefin framing, some basic principles. But if I want to look at complexity, there's a few things I need to be aware of. One is this point from Brian Arthur. So he's great fun, he's an Irishman. We compete on who met the worst people in the IRA back in the 70s if we get together over dinner. Right? This is a key point. He was the guy who actually used complexity in economics for the first time and sort of got pushed out of Stanford University as a result. The trouble with complexity deals with systems which have perpetual novelty. Everything is connected with everything else, so everything is changing. And one of the best ways to think about this is Alicia Gerara's definition. is a complex system is entangled. In fact, if you go back to it, the Latin origin of complicated is folded. And if you fold something, you can fold and unfold it. It doesn't change. The Greek origin of complex is entangled. Everything is entangled with everything else. And you can only really understand the system as a whole or by micro-interventions. Yeah? So if you try and untangle something which is tangled, it generally breaks, or you never get back to the original. Everything is connected with everything else. So basically that's the problem, but it's fairly easy if you move over to heuristics. So there are some basic principles here. First one, and these are, for those of you in philosophy, we talk about necessary but not sufficient conditions, if you know that. So without this it doesn't happen, but this on its own is not enough. Yeah? So the necessary not sufficient is key. First one is there must be many elements. There's got to be lots of things. Yeah? That's one thing. The second thing is they have to have rich, short-range interactions. And this is really important. Yeah, very short-range interactions. And thirdly, no agent must be aware of the system as a whole. So if you look at things like bird flocking, yeah, whether if you look at the murmuration of starlings, and there's a picture of that there, each individual bird is following the next bird, matching speed, avoiding collision. And from that, the form happens. If you look at antelope behavior, every antelope in a herd will actually put itself, it will identify another antelope and place itself between that antelope and the predator. And that means the herd comes together very quickly. If the antelope behaved selfishly, the herd would dissipate, yeah, and actually they could be picked off. It's a good team exercise, by the way. You put 20 people in a room, open space, and you say, identify somebody in the room who's your worst enemy and somebody in the room who's your best friend. Before you do that, you tell them not to look at anybody or say anything once after the instruction. Take videos, by the way, because you can study it afterwards and it tells you a lot about the organization. And you tell them to start off by actually protecting themselves by placing their best friend between them and the enemy, i.e. best friend dies first. Group dissipates over the room, switch the room, protect your friend from your enemy, the group clumps instantly into the middle. It's actually quite a good exercise because it shows how a very simple change in a heuristic can produce a radically different system effect. Italian drivers, by the way, south of Naples, don't follow the traffic laws. I made that mistake in Naples once. It's flocking behavior. Once you recognize it's easy, follow the next car, match speed, avoid collision, ignore everything else, and you have stress-free driving, right? So these are sort of different principles in terms of the way you work, right? Now, the other point about this, and this is going to upset some people, it means anybody who's telling you to think holistically does not understand complexity. Right? Because you can't think about the system as a whole because there are too many possible interactions. So if you start to think about the system as a whole, and you see this in systems dynamics, you see it in cybernetics, you end up creating structures which miss the weak signals. They miss the 17% of people who've seen something you need to pay attention to. So the secret on designing a complex system is lots and lots of short-range interactions with high visibility of the results, so you can reinforce the good ones and disrupt the bad ones. Yeah? Now that's actually a difficult thing to grasp, but it's a really important principle. And to me, that is the next generation of software architecture. And in many ways, it's going back to what we were doing in object orientation in the 1980s. Yeah, you have lots of small bits of code, and this is not the same as microservices, by the way, that's kind of like a subset. You have lots of bits of code, you have standard interfaces, information in, information out defined, you have polymorphism, you have inheritance, and you see what happens when these things interact with each other. And one of the things I was arguing in the 80s and 90s, and we're now building into software architecture, is that people are objects too. Yeah, one of the things I forgot to say earlier, I knew it's something I forgot, is we actually evolved to make decisions in clans and families, not individuals. Remember my point about Malcolm Gladwell? We're really good decision makers in small groups. We're really bad decision makers as individuals. And the interesting thing I'll draw on later is that 5, the extended family, the maximum number of active decision makers is between 3 and 5. So we evolved to compromise in groups of 5 or less. When you get into groups of 5 or more, we don't compromise anymore. And I'm going to draw that into a software user requirement method in a minute. So that's kind of like understanding the natural science on this stuff. So those are kind of like key principles. And I say, my view is you need human objects with software objects interacting with each other, because actually that gives you a more effective system. And effectively any application is an emergent property of the interaction of technology with people over time. It's not something you completely design up front. What we now do as designers is we design the ecosystem and we design the interaction and we design the feedback loops, and then good things can be reinforced very quickly and bad things can be disrupted. And that actually is a radical reduction in cost in software development and everything else. So those are kind of like 3 sort of basic principles. The other 3, which I'll go through, and I'm going to build a method on this in a second, is that means we need to optimize the granularity of what we're working with. Right? This is called the Goldilocks solution, if anyone remembers the story. If it's too big, it's too structured, it won't change. If it's too small, it's too fragmented, it won't work. It's got to be just right. And this is what we call the optimal level of granularity. Yeah? The easiest way to do this in a workshop, by the way, anybody who's on the S-Strime workshop yesterday will have seen this, is when people brainstorm something and they're positioning it on a framework, you say, if you can't agree where it sits, break it down to things that you can agree on. And once you've got things that you can agree on, that's the optimal level of granularity. And that's actually important in software development as everything else. Don't have an argument about something. Say, how would we break this down until we can agree what it is? Now you've got the things at the right level. That's a little trick, but it's actually quite useful. The second thing is you need to distribute the cognition and the analysis. 70% have seen a gorilla. You can't afford to have 5% deciding what we do. You need the whole of the workforce engaged in actually assessing situations so you can find outlier groups. And I'll show you a picture of that in a second. And the final one is you need to disintermediate decision makers. Now, disintermediation is an EU term. It means to remove the interpretive layers between the decision maker and the raw data. So I've built systems for marketing directors by which they can go direct from an abstract representation of their market position to the stories told by consumers when they drink their product, without any interpretive layers between them. The work we're now doing with software developers means instead of things like story points and user requirement things and all those sort of things, you have direct access to raw user experiences which you know are statistically significant to what you're trying to do. Because every interpretive layer removes weak signals from the system. And that's called disintermediation. Okay, so let's look through some principles that we can work on this. I've focused over the last 3 or 4 years in user requirement definition. And I'm going to go through 3 methods for that and then kind of like pull this to a close. So one of the things when I was first coding, and just to indicate on this, I go way back, right? The first program I ever wrote was on a 300-mode acoustic coupler at school, where we wrote a program to fake our physics practical results. Sorry, I went into theoretical physics. Practical physics is really boring. Why would I repeat experiments where I know what the result is meant to be? So we used one of the first ever school computers to actually generate tables of results so we didn't have to sit through the practical, right? So we sold it for a considerable sum to the first year 6 when we went to university. But in those days, and I was trained how to use a punch card machine. Anybody remember punch card machines? Yeah, headmaster told us we'd have a job for life if we learned how to use a punch card machine. Yeah, the modern equivalent is teaching Java code to kids in schools. And I'll make a general point here. By the time people come out of school, what software can do is going to be so radically different, anything they learn now is irrelevant. We should be teaching them anthropology and philosophy and ethics and design, because those are human skills which are going to have utility later. They can pick up the programming, it's going to radically change. Same sort of principle. And for those of you who don't know, there were 3 feeders into the Agile community, XP, Scrum, and DSDM. I was one of the 3 founders of DSDM. It was ourselves, Logica, and Cambridge. And 3 competitors put together a consortium to define standards for rapid application development. Interesting, we did it as competitors, not to get proprietary advantage. Something which the Agile community, I think, missed out on, is doing things collaboratively rather than as isolated groups with all the framework wars. Yeah? So I've been involved in software all those times. And if you learned to program on punch cards, it taught you programming discipline. Compile error on card 2 after you've queued for 3 hours to get into the computer room teaches you some discipline on coding, all right, with the use of elastic bands and Tipex. And if you don't know about elastic bands and Tipex, you haven't lived through that period, all right, in terms of the way it worked. But when I went into financial management. I was a financial director. And then I went into consultancy and started to build IT systems for people like Guinness and Vesti Group. And I was working at C-level, so these are executive decision supports. Now, decision support systems. Now, I'd actually done their job, albeit at a more junior level. And I was using a 4GL, which I had to learn in 2 weeks because the company I joined had sold me an expert at something I'd never even seen in my life before. This is the early days of computing, things like that happened, all right? So I got through that. But actually, I always built what I thought they should have asked for rather than what they asked for. Yeah? And a lot of what I coded, I developed as I was doing it, because I was coding the stuff and looking at things. I was, oh, that's a good idea. Maybe we could do this as well. Yeah? Now, that's actually what got me promoted, what got me into senior executives, what got us massive profit streams to those customers, because if we delivered what they'd actually asked for, they would have just done what they'd always done before. Yeah? By having somebody who actually knew coding and knew their job working, and that was all in my brain and my body, by having that working together, we could produce things they hadn't thought of. Yeah? So that sort of principle has been there all the way through. Now, that's more difficult these days. It may be one of the uses of low code. I'm not sure it's really a product of ChatGPT and things like that. I'm nervous about that in that use. But I think low code is one of those principles. But we can substitute for that. So if we're looking at software design, we now use what's called an entangled trio. So we put together 3 people. Yeah? One is a very bright young programmer who can throw things together very quickly. You know the type. They can't talk with ordinary mortals. Yeah, their fingers have a symbiotic relationship with the keyboard, and they don't spend much time apart from it. I mean, you know the type, right? So we couple them with somebody, this is called transgenerational pairing, with somebody older who's a systems architect or an end system tester. So somebody who's got a lot of practical experience, knows the consequences of things. And the third person is a user trained to talk to IT people. It's a lot easier to train users to talk to IT people than train IT people to understand users. And so what we do is we throw 10 or 15 of those trios at a problem part-time for 3 weeks and see what they come up with. So what we've got is lots of agents working in parallel, which is a key principle of complexity. Lots of different diversity in the system. We're using that to generate stuff rather than one guy going around and interviewing people about what they want. Yeah? And that's a trio-type method. Yeah? The other method we're doing a lot of now is to actually capture continuous stories of user experiences on a day-to-day basis. This is a Gemba system. So it's kind of like what frustrates you, what would you like to do? And then we statistically look at the patterns in that, and then we throw a cluster of user experiences to a group of programmers and say, could you do something about that? And that's called managing using existing technology for unarticulated needs. Now, those 2 methods radically change the nature of the upfront interaction. They also, if you think about entangled trios, they create dense networks between users and IT people which have high utility downstream. It's the informal networks which make things work. Now, there's more I could go into on that, but I need to sort of finish and give you some time for questions. But that's an example of the sort of principle we're starting to work on, is you change the input in order to actually manage the output better. On a global scale, by the way, in a big program we ran for the EU, one of the things we're looking at in terms of how do you handle fake news is to manage the input into the system rather than to have algorithms to interpret the output. Now, I'll make this as a general point. It's the old garbage in, garbage out, which everybody quotes, but everybody's forgotten. We need to focus far more on the input into a system and far less on the output of a system, because the world is increasingly complex and we need to relate to that. And that leads me into the final thing I wanted to briefly talk about, and this is to make the point. So you've all seen one of these things. Yeah, it's called a bell curve. Everybody remember bell curves? Yeah, all God's children love bell curves. All right, the reason we like bell curves is that we can eliminate the outliers. And then we can define practice in the middle. If you look at things like safety rules, coding rules, distribution rules, clustering rules, they all tend to follow this process. Now, the problem with this is that if you actually have any human system and you do a double log scale of size against frequency, you get a pattern which looks like this. I can draw a straight line through it. It's not straight there, and that's significant. This is called a power law. Yeah? So the blue line is a type of Gaussian distribution. If I overlay that, which is a Pareto distribution, on the Gaussian distribution, I get this. I've now got the famous fat tail. This is the stuff Taleb talks about, but actually Didier over in Zurich is much better on this stuff. Yeah, basically the things I thought were very unlikely turn out to be more likely than I thought. Yeah? Now that's one of the problems. So we've done work, for example, on safety, where we've shown the main cause of mental breakdown is actually not the job, it's the safety rules. Because the safety rules have been designed on a past study and fitting things to a normal distribution to define the rules in advance. Reality exists in the tails of a Pareto distribution, so reality doesn't conform with the rules. Yeah? I'll bring this back to complexity to finish in a second. Now, if I look at this, then actually here, this is ordered. I've got a many-to-many relationship. Everything which happened in the past, and nothing was going to happen in the future which didn't happen in the past, so I can use the past to make statements about the future. Yeah, no problem with that. Best practice. As I come here, this is now becoming significant. So although a lot of things which happen in the past repeat in the future, they increasingly mutate and there's increasing novelty. But I can still make statements about the future based on my understanding of the past. Yeah, this is where we do scenario planning, cone of possibilities, contingency planning, all those sort of good things. And up to this point in the system, what we're doing is called inductive. We're using cases, what we understand about the past, to inform what we do in the future. And that's the basis of virtually every management book and every method. Nothing wrong with that, it's inductive logic. The trouble is, when you move out here, everything changes. So you've got constant mutation or constant novelty. So using the past to manage the future is actually very dangerous. And this is where you move into what is called abductive logic, not inductive logic. And at this point, and this is really coming back to it, this is truly complex. At this point, I can't actually determine in advance what the right thing is to do. So what I have to do is to create a process which can actually manage the uncertainty and manage the emergence. Now, I've given you an example with trios. Let me give you another example. Work we're doing on decision making now. If 3 roles make a decision, for a financial decision, it stands. Not an individual, we delegate into a role combination. We can randomly allocate people who satisfy the conditions for that roles into the group. One of the members of the trio can be anonymous, so nobody knows who it is. And so we can allocate very large sums of money very quickly in real time without the need for bureaucratic control processes. The same is true of software design decisions. By actually shifting decision-making into role combinations of people from different backgrounds, we can reduce the energy cost of decision-making, but critically, we can manage complexity by making decisions as they need to be made, rather than having to reference up and reference back. Okay, so what I've been trying to do here, I came back to where I started, is to say, look, there's a lot of new methods and tools we can adopt and use here. There are different frameworks, different ways of working. But inherently, we need to understand that to manage uncertainty, we can't actually have a linear flow. We've got to have processes which distribute decision-making and distribute capability so that we can make decisions very quickly. And in software development, that means finely grained objects, distributed cognition, and the ability to very quickly apply resources as things start to work. So we define the things, we define the interactions, we define the monitoring. As things start to work, we reinforce them with more energy. If they start not to work, we disrupt them in terms of the way we work. So we manage an ecosystem of possibilities rather than a manufacturing flow to give people what they thought they wanted, but they probably won't need. Thank you very much for your time.